Okay, here I am again with my wonky technological setup. Okay, so this is the rest of the slides. So just to remind you, this is a battery and this is a capacitor. And a battery's job is to keep a constant potential difference between the terminals. So if you have, sometimes we talk about cells. One cell is 1.5 volts. And so you can label the bottom, the negative, this small guy is the negative terminal. I guess that would have been nice if I'd done that in there. That's a negative terminal, that's the positive terminal. And you can see the positive terminal of the battery is at a higher potential than the negative terminal. So we usually just label the bottom one, the negative one, 0 volts, and the top one, 1.5 volts. There's obviously, you can choose your 0 anywhere, but you're gonna have a lot easier time if you just think about it this way. Okay, so what happens if you connect these? So here's some wonky wires that I threw in there. The bottom plate will become negative and the top plate will become positive, and the voltage between them will be 1.5 volts, right? Where V is what we're going to call this voltage across the capacitor, okay? That 1.5 volts is now our V across the capacitor, okay? So there's our negative charges, there's our positive charges. Again, what's going to really happen is when it says positive charges are on here, it's really because negatives went to the battery, right? And that if this is now more positively charged, then obviously negatives from this terminal are going to be attracted to them, and so they'd come over here. So that's how it actually gets set up. And admittedly, they don't talk a lot about that in AP, but I figured you guys would want to know what's really happening. Okay, so again, top plate will have charge plus Q and bottom plate will have charge and negative Q. How much charge shows up and gathers there depends on the capacitance. And remember that capacitance is the geometric factor, right? That how these plates are arranged. So that amount of charge is going to be equal to the capacitance times the potential difference between them. So this is a kind of thing that they do a lot. They say, now I change the capacitance. So that can happen a couple different ways. If it's just a parallel plate capacitor, remember that the capacitance was epsilon naught A over D, so I can change the area, or I can change the distance between the plates, okay? So, what will change if I change the capacitance? Okay, so here's my C. I change this. What else is going to change? It depends. This is a pro tip. If the capacitor is connected to a battery, then the potential stays constant, right? That's the battery's job, is that it's going to keep that potential constant, all right? So to answer the question, if the capacitor is connected to the battery and say I increase capacitance by either increasing the area or decreasing the distance, then I will get more charge. My Q increases, right? Looking at Q equals CV, that should be good and clear. Okay, so there's my V stays constant, my C increases, so my Q increases. Now, the other thing that can happen to a capacitor is, remember in that FET lab, you could cut off you could like disconnect the wires, right? And so if the capacitor is isolated or disconnected from the battery, then the charge has nowhere to go, right? So if the Q is staying constant, right, looking at this equation again, if Q stays constant and my capacitance increases, then my V will have to decrease. Okay, cool. You should go try it with the FET and verify these. I think playing with that FET can be very useful in terms of getting your intuition going. All right. So another really important thing, we actually started this whole conversation saying a capacitor is something that stores electrical energy. And that energy is given by this. Okay, so you're going to want to calculate it at some point. So there's a couple different ways of writing it. 1/2 QV, 1/2 CV squared, Q squared over 2C. Use science bowlers. Those are a lot of times useful. So question is, what is that energy, right? It's the potential energy of the system of charges in those positions, right? You have some positives and negatives that are held apart from each other, right? And when we talk about that potential energy of the system, very often we talk about how much work it took to place those charges there, right? So that's a little buzz phrase that you see in these questions. How much work did it take to arrange these charges to where they are now? And that ends up being equivalent to that potential energy, okay? So U equals QV sitting right here, right? That's your potential energy. But hold up, that says 1/2 QV. So why the 1/2? So feel free to pause this and think before I tell you the answer. It's really easy to place the first set of charges on those plates. But then it gets harder and harder and harder as you're shoving. Think about how hard it is to get that last charge, right? Or set of charges, really, it happens at the same time, onto those plates. It gets harder and harder and harder. So if it starts out easy, gets harder and harder, hopefully your brain is going to an integral. So there it is. So each little amount of work that I do for each charge, I can add those up, right? And that's V dq. Sorry, I guess I could have written that in there too, sorry. Q over C is V, right? So each little charge, when I start at 0 and I get all the way up to big Q, right? And so when I have an integral Q dq, it's 0 to Q, sorry, big Q. There's your Q squared over 2C, okay? So my question to you now is, what happens to the energy in a capacitor if I increase the capacitance? So hopefully you're going to look at those equations and see that U is proportional to C, or U is proportional to 1 over C.